Hello guys, I am Kalidas Tapada. Welcome to Quality and Welding Metallurgy. Today we are discussing on recommended practice for welding of chromium-molybdanium steel piping and tubing as per American Welding Society AWS. This recommended practice apply to the arc welding of the following base metal combination. First, similar chromium-molybdanium steel, dissimilar chromium-molybdanium steel, chromium-molybdanium to austenitic chromium nickel stainless steel. 4. Chromium-molybdanium to either carbon or carbon-molybdanium steel. In the document, the chromium-molybdanium steel alloying are referred to as CRMO steel. CRMO steel are used extensively in the power, chemical and petrochemical industry. The property of such piping and tubing material and the applicable fabrication and inspection requirements are addressed in the wide range of the documents, including ASME material specifications, ASME code for pressure piping B31.1, power piping ANSI ASME B31.1, chemical plant and petrochemical refinery piping NSI ASME B31.3, ASME boiler and pressure vessel code section 2A, 2C and 8 and 9. NBC National Board Inspection Code for Boiler and Pressure Vessel NSI NB23, API Piping Inspection Code, Inspection, Repair, Alternation and rating of the service piping system API 570. Base metal. General Table 1 listed the type of steel considered and the nominal chemical composition and abrasion by which they will be identified in this document. If material not listed in Table 1 are used, the contents of this document may not apply. This will be especially true if the hardenability is increased by the presence of the higher carbon content. The carbon content of the material listed is usually below 0.15%. The primary factors governing the choice of the filler metal are the composition of the base metal to be joined and the service condition of the system. Generally, the filler metal composition and the mechanical property of the deposited weld metal should match those of the base metal as closely as possible. Where service including corrosion or oxidation, the corrosion and oxidation characteristics of the base metals and the weld deposit should be either matched as closely as possible or selected to minimize galvanic reaction. Table 1 Base metal abbreviation. Base metal addition. Since the last edition of this recommended practice, one new chromium moly alloy has been added. It has a nominal composition of 9% chrome and 1% moly, but vanadium, niobium, and nitrogen have been added to improve mechanical properties and corrosion resistance at elevated temperature. This new material has been assigned in grade designated of P91 and T91. Its weldability is similar to that of the conventional 9-chrome moly material. Specially filler material have been developed for some welding process. General suggested filler metal for various base metal combination are shown in table 2. The filler metals in the table are listed in accordance with the AWS classification for electrode and rod for the shielded metal arc welding SMAW, gas tungsten arc welding GTAW, gas metal arc welding GMAW, and flux cored arc welding FCAW process. The classifications of filler metal for both processes will be in accordance with the specification for those specified process. Until recently, the 5, 7, and 9 chrome MO, CRMO electrode and filler metal had been included in the ASME AWS filler metal specification as austenitic stainless steel and had been assigned classifications such as E502. Recognizing that these filler metal are basically low alloy steel, their classification have been transferred to AWS's low alloy steel filler metal specification and have been assigned classifications such as E8018B6. During these transitions years, welding procedure and filler metal inventories can be expected to use both classification for the convenience of the user. Table 2 of the document lists these electrodes with their respective old and new classification. Cromium-Molybdanium piping systems are usually selected for corrosion resistance, higher temperature creep strength, or both, since corrosion resistance is often associated with maximum hardness. Low carbon electrode like E8018B3L, which are laser air hardenable, are frequently selected for such applications. However, if high temperature creep resistance is a major design consideration, minimum carbon level may be required and minimum percent carbon such as 0.05% may be specified by the user. Low hydrogen to reduce the probability of cracking. Low hydrogen practice should be followed potential source of the hydrogen should be minimized or eliminated. This means both removing moisture and other hydrogen containing materials such as cutting oil from the surface of the base material and using clean and dry filler metal and shielded gases. The moisture contained of the filler material must be kept low by proper manufacturing, packaging, storage, and usage procedure, or by redrying and cleaning. All low hydrogen electrodes exposed to the atmosphere for time in excess of the recommended time period should be recommended according to the manufacturers and recommendation. Sorry. Moisture control is of the special concern when the joining two different base materials. While it is common practice for the electrode to match the chemical composition of the lower alloy material, the moisture limit should be based upon the higher alloying ferrite base metal. This is because higher alloyed and higher strength ferrite steel are more susceptible to hydrogen induced cracking. Since most austenitic stainless steel and nickel alloy electrodes are likely to contain more moisture than many chromium-molybdanium steel electrodes, it is advisable to carefully rebake such electrodes before they are used for welding chromium-molybdanium steel. The time during which low hydrogen electrode may safely be exposed to the atmosphere and thereby observe some moisture can be extended by the use of electrodes whose conveying have been specially designated and processed to reduce the rate of the moisture observation. For electrode meeting such requirement, AWS provides an R designator like E7018R and E8018B2R. If contamination is observed or suspected, the following using action are suggested. Atmospheric moisture observation by shielded metal arc welding ASMAW electrode or submerged arc welding SAW flux may be corrected by rebaking the material in accordance with the manufacturer recommendation. Should this information not be available, the user should be determine an appropriate rebaking procedure. As a starting point, rebake a small quantity of SMAW electrode at 700 degrees Fahrenheit, 370 degrees centigrade for 1 hour. Since rebaking may reduce the bond between the covering and the core wire, the user should determine if additions of the coating to the core wire has been damaged or if welding operability has been adversely defected. If so, the rebake temperature will need to be reduced. SAW flux should be rebaked for 1 hour at about 600 degrees Fahrenheit, 315 degrees centigrade. For electrode and fluxes, rebake temperature below 500 degrees Fahrenheit, 260 degrees centigrade are not recommended. Suggested filler metal for various base metal combination. Low hydrogen SMAW electrode or SAW fluxes should be discarded if contaminated with material such as hydrocarbon or exposed to water such as left in the rain. Moisture in the bare solid wires may be removed by heat or clean dry air. Hydrocarbon on bare solid wires may be removed by degreasing, rinsing, and thoroughly drying. Spools and coils may require rewinding. Backing ring and consumable inserts. The chemical composition of backing ring and consumable insert usually is similar to that of the filler metal. Although lower alloy composition have been used successfully since a lower alloy composition of the backing ring or consumable insert may be reduce the corrosion and creep resistance of the weld. It should not be employed without first reviewing the service requirement of the fabricated part. Such a review is also necessary when the temporary backing rings are used because the dilution of the weld metal by the backing material affected the chemical composition of the final weld. Backing rings and consumable insert application. Application of the filler metal showing in table 2 are following. Joining similar steel. In addition to matching the composition and mechanical property of the base metal as closely as practical, the chromium and molybdanium content and the tensile strength of the weld metal should not be lower than the minimum value specified for the base metal. Joining dissimilar ferritic steel. Where dissimilar metal are being welded, the only 4 possible filler metal compositions are: number 1, the lower alloy base metal composition. Number 2, the higher alloy base metal composition. Number 3, intermediate composition, or number 4, a composition different from any of the first 3 where both base metal are ferrite. The fourth possibility maintained above, that of an entirely different alloy, is of special concern for service at elevated temperature or in corrosive environment. Consistent with the factors listed above, this fourth possibility should normally be considered only where one of the base metal is stainless steel or nickel or copper alloy. Joining dissimilar ferritic steel where only ferritic metal are being joined, good service results have been achieved with all of the first three possible ferritic filler metal composition. However, the majority of the users select either a lower or an intermediate composition of filler metal for butt joint because the well metal does not need to stronger or more resistant to corrosion or creep than the lower alloy base metal. Table 2 follows the aforementioned concept. Exceptions are advisable in the case of the support, hanger tube, and similar part attached to the piping or tubing system. Filler metal should then be selected to match the mechanical and chemical properties of the pressure retained part in the order to compensate or dilution during welding. Joining ferritic to austenitic chromium nickel steel. When joining ferritic steel to austenitic chromium nickel steel, the composition and properties of the well metal represent a mixture of the two base material and the filler metal. A consideration of the result and mechanical, metallurgical, and corrosion resistant property eliminates the use of the following: ferritic filler metal or austenitic filler metal of approximately 18 chrome 8 nickel composition. Since the resultant diluted well metal will be martensitic with lower ductility and increased cracking susceptibility. Fully austenitic stainless steel filler metal such as type E3010, since this may produce well metal with micro cracks which can propagate into the serious cracking. 3 number higher nickel alloy electrode with titanium addition such as NiCrFa6, which will be produced well metal deposit with over 0.75% titanium, since this may edge harden during subsequent heating operation. Successful welds have been made with the type E309 stainless steel filler metal, which are slightly ferrite number 2 to 10, and contain sufficient chromium and nickel to compensate for dilution. However, well deposit may be contribute to thermal stress or fatigue problem if the weld is exposed to the thermal cycle service or to temperature above 600 degree Fahrenheit, 315 degree centigrade. This is due to the pronounced difference in thermal coefficient of expansion between the ferritic base metal and the austenitic stainless steel. The thermal stress which are produced may exceed the yield point and can initiate and then propagate cracking at or near the fusion line. In addition, at elevated temperature, carbon migration from the chromium-molybdanium base metal to the 300 series stainless steel weld metal, producing a decarburized zone that has weakened and can shorten the life of the joint. Thermal stress between ferritic and austenitic base metal cannot be eliminated or even reduced. However, they can be distributed over a wider area with a weld metal whose coefficient of expansion is intermediate between the two base metals. Nickel-based filler metal containing about 65% nickel, 15% chromium and 12% ferro meet this requirement and are capable for producing a weld metal that is metallurgically and mechanically sound. Furthermore, they reduce carbon migration from the chromium-molybdanium base metal. Typical AWS classifications for this type of filler metal are ENiCrFe2, 3 or 4. ERNiCi3, however, nickel alloy are less resistant to high temperature sulfur corrosion than the higher alloyed chromium-molybdanium steel. And all austenitic stainless steel. Furthermore, high nickel alloy often call for different welding techniques and joint design. Since these filler metals have less fluidity than austenitic chromium nickel stainless steel. Use of transition seams of buttering. Use of transition section and buttering where dissimilar metal are to be joined. It is sometimes better to avoid a butt joint between the two base metals. This can be accomplished either by interposing a short transition section, sometimes called a safing, or by buttering one of the metal with the filler metal before proceeding to weld the butt joint. These procedures are commonly used when the post-weld heat treatment is required, one of this base metal and not the other, or to avoid a field heat treatment operation. For example, when a ferritic base metal is to be joined to an austenitic base metal, this heat treatment can be determined to the austenitic base metal due to the embrittlement by sigma phase. This can be overcome by buttering the ferritic side of the joint with a nickel-based alloy. This would be followed by the heat treatment. The weld between the buttered end and the austenitic stainless steel will not require heat treatment. The same reasoning applies to the two ferritic metals where only one of them requires heat treatment. In this case, however, the transition section of filler metal should be an iron based alloy rather than nickel based alloy. Other filler metal. This filler metal listed in table 2 are not necessarily the only one suitable for such welds. Other filler metals may well be proven acceptable by procedure, qualification, and service test. The table listed electrode and rods for the SAW, GTAW, GMAW, and FCAW process, where other welding processes are used. Filler metal of equivalent composition and properties should be selected, provided that the dilution will this process produce equivalent weld metal composition. Thank you. To be continued.